Welcome to 6.3, where we're going to be talking about periodic trends. Now, this section is really where the power of the periodic table comes into play because, again, the periodic table's power is in the ability to predict properties of elements, to predict how these things are going to behave. Now, again, the term periodic means repeating at regular intervals. And so whatever trends you find moving across the periodic table, as soon as you get to a new row, those properties are going to be starting over and then repeating themselves as you move across the row from left to right again. And then as soon as you start a new row or period, you're going to get a repeat once again. And so we're going to be taking a look at least three different types of trends and showing you again how these things repeat as they move from left to right and down the periodic table. The first trend that we want to look at is trends in atomic size or radius. Now, the problem with measuring the size of the atom is that the electrons are not fixed, and in fact we don't know exactly where they are. We treat them as probabilities, or we deal with them in terms of their probabilities. So if this is the nucleus of an atom, we cannot say for sure that that is the outer boundary of the atom, because remember, the electrons are simply a probability area, so you can draw a cloudy area, but then that cloud just kind of dissipates as you move outward and more outward. So there's really no hard edge to the atom. There's no outer boundary to where the electrons can go. So how do you measure the size of the atom? Well, what we do is we measure what's called atomic radius. Now, of course, a radius, just like when you're doing the radius of a circle, the radius is the distance from the middle to the outer edge. Well, since we don't have an outer edge, what we do is we measure the distance between two nuclei when the same element is bonded to itself, and then we arbitrarily say that the halfway point will be the outer edge. Now, is that actually the outer edge? No. In fact, there's a slight overlap to these atoms, but this is simply a definition. So, once again, the atomic radius is going to be 1/2 the distance between the nuclei of the atoms of the same element when the atoms are joined. Okay? And so you can see how small these things are. 30 picometers for hydrogen, up to 140 picometers for iodine. That's incredibly small. All right? Now, we're dealing with repeating trends. What happens to the size of the atoms as you move from left to right and down the periodic table? Well, this might surprise you. You might think that as you add more stuff, as you go across the periodic table, that the atoms would get bigger. But in fact, the opposite happens. This is crazy. As you go from left to right on the periodic table, the atoms actually get smaller. Notice what happens in period 2. Here's lithium. Here's neon, the last atom in the row. As you move from left to right, the atoms actually get smaller. Now, why would the atoms get smaller as you're adding more stuff? Lithium has 3 protons, 3 neutrons, and 3 electrons. Neon has 10 protons, 10 neutrons, and 10 electrons. So there's more than 3 times the amount of material in neon, yet it's smaller than lithium, and it follows that trend all the way across the periodic table. So again, what's going on here? Well, as it turns out, most of the atom is actually empty space. If you recall from previous discussions, if the nucleus of the atom is the size of a garden pea, then the rest of the atom, the electrons, would fill up a football field. So if you take a garden pea and stick it in the middle of Ford Field or Michigan Stadium or Spartan Stadium, the electrons are all the way out in the stands. Most of the atom is empty space. So simply adding more material to the atom does not make the atom bigger. But what happens as you go from left to right is the nucleus gets stronger. So if this is lithium, I'm going to go over to the right-hand side here. Here's the 3 protons, and again, here are the 3 electrons. And this is obviously not to scale, but we'll just draw it like this. Okay? This would be the size of the atom of lithium. I'm just going to draw a circle just in a general area, something like that. Okay? But now as you move across, what happens is you add another proton. As you add another proton, the proton, even though you're adding another electron as well, the extra proton starts to draw the electrons a little bit closer, a little bit tighter. The nucleus is stronger. As you add another proton, it draws the electrons even closer. And so on and so forth. So by the time you get to neon, neon has 10 protons, and though it has 10 electrons, those 10 electrons are drawn much, much tighter to the nucleus than lithium. The way you want to think of it is not the fact that neon has more than 3 times the amount of material. The real thing here is that neon's nucleus is more than 3 times stronger than lithium. And because it's more than 3 times stronger than lithium, the electrons are going to be drawn even tighter to that nucleus, and so it's going to contract. So as you go from left to right on the periodic table, atomic radius, I'm just going to label it AR, atomic radius is going to actually decrease. That's counterintuitive, but that's actually what happens. Now, what happens as you go down the periodic table? As you go down the periodic table, the atoms do in fact get bigger. Notice lithium, sodium, potassium, rubidium, cesium, those are all alkali metals in row 1. And so as you go down the periodic table, the atomic radius, AR, actually increases. Let me scroll down just a little bit. Now, why does it increase? The reason why it increases is because every time you start a new row, you're starting a new energy level. Lithium has the second energy level. Sodium starts the third energy level, and by definition, that third energy level is further away from the nucleus than the second energy level. Potassium starts the fourth energy level, rubidium starts the fifth, and cesium starts the sixth energy level. The electrons are being pushed out further and further away because the energy levels are further away. It has nothing to do with the amount of material that's there. It has to do with the energy levels and where the electrons are located. And so, again, if we make an analogy over here on the left, if this is lithium, the reason why sodium is bigger is because the third energy level is further away, so the electrons get pushed further away. There's only one more proton and one more electron than neon, but yet it's much, much bigger because that electron is further away. Potassium is bigger because the fourth energy level is further away. Rubidium has the fifth energy level, and finally cesium is in the sixth row, so it has a sixth energy level. So, just in summary, in terms of atomic radius, as you go from left to right, the atoms get smaller because the nuclei get stronger. As you go down the periodic table, though the nuclei still get stronger, you're adding a new energy level. And because you have that new energy level, the electrons are pushed further away. Let me just back up just for a second. As you go across a row from left to right, the electrons are not being placed further and further away from the nucleus. They are all going into the same energy level. Either they're all going into the second, or they're all going into the third, etc. And so because the electrons are not being placed further away, the stronger nuclei can draw them closer. But as you go down the periodic table, the electrons are simply being placed further away, and that automatically makes the atoms bigger. All right. In the next podcast, we're going to take a look at ion size and ionization energy.